Okay, so just I present you and I say some words and so dear community, I would like to thanks to all the participants of this seminar, especially the speakers and all the attendants of each talk. With this section, we close this part of the activities planned for the Seminario conference in 2023. We will have one more activity prelude with a student school, which I will send the information soon. We expect to be in touch and that this area grows widely. We're happy for networking appearing recently, and we hope new interesting questions born by these activities and in the future could be solved. On this occasion, we have the pleasure to have as speaker Professor Julia Seminika from the University of Münster. She will be talking to us about the beautiful subject of Schneider-Nucleven, with her talk on Q and space spectrum on manifolds K1 invariant in relation to BCob. Thank you very much, Julia, for accepting to participate. The time is yours.
Thank you very much, Carlos, for organizing such a nice series of talks and the whole seminar. And it was the best introduction ever. Nobody yet called me professor. I am very flattered because I'm not. I am not a professor yet. The topic for today is cut and paste spectrum of manifold. And we will talk about its K1 and how it relates to BCob. So somehow I will also a little bit rely on the previous talk by Renee, where she introduced K-squares and K-cubes. I will remind you, of course, the definitions of all of that. And I want to say that this is work in progress with Mona Merlin and George Raptis. One second. So we are still working on that, and the paper is not appear on the archive next week. So there will be some still open ends of what I say, but still there are already some bunch of results that extends what was spoken about before. So what I will tell, I will first remind you what are K-squares of manifolds, what we know about certain elements in K1, how we can explicitly trace them under the map to algebraic K-series of integers. And I will also show you some nice maps of spectra, like coming from category with squares. How can you see sphere spectrum sitting inside our K-squares? So this will be the first part. Then we will talk about variations of these K-squares where you can take into account topology. So Renee also talked about this a little bit. So mostly in the context of K-cubes, but I will focus on the topological version of squares first, and we'll show you how to relate it to the usual BCob. And then we will proceed to K-cubes, and we will get the missing sequence of spectra between K-cubes and also BCob, but one dimension higher. So you'll see. So the previous talk was somehow, the talk by Renee was also called like cut and paste in relation to cobordisms, but there are different relations with cobordisms. One is kind of constructing a spectrum where you take into account directions that correspond to cobordisms, but then you can also compare this spectra that you constructed to just honest cobordisms without saying that there is a direction of cobordism. So this is a plan for today, and we start with k-squares. So let me just tell you a few words that we've already heard from René. So the whole story was somehow inspired by something very classical, by Caesar congruence problem in Euclidean spaces, where even though the problem is very classical, there are still open questions about what are invariants of Caesar congruences. And then it was Inna Zakharevich who noticed that somehow this class of problems, of cut and paste problems in different contexts, they are all related to some versions of K-theory. And we should also maybe give some credits to Goncharov for this, because he has like a nice paper where he writes exact sequences relating classical Caesar congruences to K groups. So this was an observation of Inna. And then together with Jonathan Campbell, they constructed a nice spectrum that encodes this cut and paste datum for different contexts. And this is what we used, and René explains this to define K-theory, K-squares of manifolds. So let me remind you how it was defined, because we will use it to study it further. So K-squares of manifolds. For us, manifolds are allowed to have boundary. They have to be compact, and they are smooth and oriented. And we are just in this class, and we will not mention it again. So to define this, you have to construct a bisimplicial set. And let's denote it such that everything looks shorter, just b dot dot. So two simplicial directions. And the set of KL simplices, so B, K, L, is defined to be the set of all possible diagrams of the size K times L, where the datum of pasting together this number of manifolds with boundary is encoded. So let me write you the diagrams that we look at. Well, it will take a few seconds. And so last part. So it's a diagram that consists of K times L small squares. Here they are. Each point, each node in this diagram is a manifold with boundary. And each square has to be a push out of nicely embedded into each other manifolds. So let me just show you an example. Well, we already saw it in René's talk, but just to remind you, let me show you an example of 1 by 1 square, which is also 1 simplex. So that would be an example of what is allowed to have as building blocks for our diagrams. And MEMSA, so you include this cylinder like this, and then it also sits as a gluing part. And we require that each of the square is a push out of spaces. So why do we say spaces? Because we don't want to think about what is a push out in the category of manifolds. So we just say that these are literally pasting pieces of manifolds together as we would do it if they were spaces. So this is our condition. If we look at this bisimplicial set, that's encoding the whole possible diagrams, how you can paste manifolds together in this allowable way. What we do next, we take its geometric realization and takes loops based at empty set, empty manifold. And this is what we define to be k-square manifold space. So this is loop space of this geometric realization. So why did we take loops, extra loops? Because space is connected. So without taking these extra loops, it would be just it would have trivial binomial. So this is a construction, and by design and by what Renee also explained, we have that zeros homotopy group of our squares is skn with boundary. So these are those cut and paste groups or manifolds that we saw in the previous talks. That was a question? No? Okay, no questions. Good. So next step that was also covered in the previous talk is that we have a map from k-squares of manifolds to k usual algebraic k-series of integers. So we have this map. And how to see this map on the level of category with square. So we don't just, it wouldn't be enough for us just to have a map of spectra, but it really is coming from the level of categories with squares. So if you want to see this, we should map it to k-squares or homologically bounded chain complexes over Z. And how is this a category with squares? So it's a general fact that you can find in our very first paper, that if you have a Waldhausen category C and the category of homologically bounded chain complexes is such category, Waldhausen category. So you can equip it with the notion of squares. You can make it into the category with squares. And it's not actually important to remember what is a category with squares, what axioms are and what conditions it should satisfy. So at this point, just believe me that there are some nice conditions for the notion of squares. So whenever you have a category, the extra datum that you want is certain notions of diagrams that are squares one by one that are of the shape. And squares in Waldhausen category, they are defined to be the following. So you look at all diagrams where horizontally you allow cofibrations, vertically you allow all maps, all morphisms from your Waldhausen category. And you look at those diagrams that satisfy the following property. So you take a push out here, and push outs along cofibrations exist in Waldhausen's category. So this is a push out. And there is a map from this push out to object T, and you require this to be weak equivalence. And by definition, these are our squares that equip C with a datum of those squares. So if this holds, one can check that push outs of manifolds exactly go to diagrams of squares of chain complexes that are of this shape. They are push-outs up to weak equivalence. And then this is a map that just take a manifold and sends it to its singular chain complex with coefficients in Z. And this gives us this purple map from k-squares of manifolds to k-squares of chain complexes. And this is also fact that we showed that if you equip Walthausen category with such datum of squares, then it gives you the usual algebraic K-theory of Z. So this map exhibits Euler characteristic, by which I mean that if you restrict it on pi naught, then we know that on the left-hand side, we have SKN boundary groups. On the right-hand side, K naught of integers is just Z. We have an induced map, and it takes the class of a manifold to its Euler characteristic. So this is what we had last time. And now we want, let's see. Okay. So now we want to look closer at this spectrum. And first thing that we can see is that sphere spectrum sits as a direct summand in this k-squares of manifolds. How to see this? So this is our first part of the theorem. So let's first recall that we know that a sphere spectrum can be obtained by applying Walthausen's K-theory to category of finite pointed sets. So this is a Barat-Pridy equivalence theorem. And if we look at how to translate finite sets into, so Walthausen category into category with squares, what we would obtain would be something like that. Squares should be given by diagrams of the shape like this, where horizontally you have injective maps of sets. So A denotes a set with A elements, B with B elements, and so on. So these are finite sets. And this should be a push out. So push out of finite sets, and horizontally you have all, you allow any morphism of finite sets. And what is a simplest idea that comes to anyone's mind? So if you want to send a diagram of finite sets like this to somewhere in the world of manifolds, what can you do? You can start with a finite set of A elements, and you might want to send it to A copies of some manifold. So you fix your favorite manifold of dimension n, any, and you fix it for the whole time being. So you're not allowed to change it. So this is fixed. And you might want to say that, okay, like it looks like you want to permute manifolds, and this would be your map. But there is one problem. So if I do this, if I just send a finite set to A copies of some manifold, if I look at the square in finite set, at this push out square, it would not go to push out squares in manifolds in the sense that this will be squares that are not allowed for the following reason. If you look at these vertical maps in sets, they are all maps, any map, so not necessarily injective. And then it will give you something non-injective on manifolds, and this is not allowed. So when I started, I told you that all the maps in my diagram of push out, they should be embeddings, they should be injective. So there is a fix for that. So this is the first idea that you might want to try. So the fix would be if those vertical maps, they were injective, this map would work. But the question is it the same, is it also a sphere spectrum? Does it give the same spectrum if we apply k-squares to this notion of squares? And the statement is yes, it is. So it's not something general for any Waldhausen category. It just happened to work in this specific case. So finite sets are so nice that if I apply K-theory with squares construction to the category that I denote finite sets injective, which means, well, objects are still finite sets, but the notion of squares are push-out squares, where all horizontal and vertical maps are injective. Then this gives me an equivalent spectrum as if I were just looking at k-squares of finite sets with the notion of squares that I first told you. So the one coming from Waldhausen category. So this is still a sphere spectrum, both of them. And then you apply this map that this very easy map that sends a push out of finite sets where everything is injective to the corresponding copies of some fixed manifold. So it's kind of permuting copies of manifolds in one component. So I have this map to k-squares of manifolds. And here there was a choice. So I said, you fix your favorite manifold M and you do this. And if it happens that your favorite manifold M was a disk, n-dimensional disk, then there is a map backwards that exhibits S as a retract here. So there is a map backwards from manifolds to a sphere spectrum, and this composition splits S as a direct sum in k-squares of manifolds. So this is observation number 1, that we have this map that sees a sphere spectrum inside our k-squares. Now let's talk about what can we say about K1 of our spectrum. So I claim that if we are given a pair manifold and diffeomorphism of manifold, then we can construct a certain non-trivial element in K1. And you should think of this as an analog of the statement that in the usual algebraic case theory of a ring, classes in K0 are given by projective modules, and classes in K1 are given by automorphisms of projective modules. And this is somehow imitation of this intuition. So whenever we have some diffeomorphism of a manifold, we can do kind of the same construction as takes place in classical algebraic case theory. So let me explain you how to explicitly see this element in K1. So I will be a little bit cheating here for the purpose of simplifying the presentation. So I will write you an element that is not exactly allowed in oriented case, but it would be completely fair if in our spectrum we would allow maps that are not necessarily orientation preserving, so still smooth but not orientation preserving. And there is a way to write much more complicated sphere, but let's just agree that maybe for this statement we work in unoriented case. Well, yes, not orientation preserving case, because it's much easier to see how this element looks. So whenever I have a pair, a manifold, n-dimensional manifold, and F diffeomorphism of this manifold. So now I will present you a construction. So element in K1. So what does it mean to be an element in K1? Remember that we defined our space as loops of some bisimplicial set. Oh, sorry, loops on the realization of some bisimplicial set. So if I want to see some element in pi1 of that, it's the same as seeing some element in pi2. So this is the same as element in pi2 of realization, in geometric realization of that bisimplicial set. So what I will be now constructing is some sphere, some explicit construction of a sphere in the geometric realization of this bisimplicial set. So for this, I have to consider just two simplexes. So simplex number one will be the following. I'm sorry. So I don't have any vertical directions, I only have horizontal directions. And this is, so often it's tempting to go to the diagonal of the bisimplicial set and just to work with simplicial set instead. But in this case, it's really, it's beneficial to work with bisimplicial thing and not to go to the diagonal. And then you see these elements in a much nicer shape. So this is 0, 2 simplex in geometric realization. Oh, sorry, in bisimplicial set. Then a simplex number 2 that we want to consider is the following. It's 1, 1 simplex of the shape like this. You look at the square that only has empty and M, and F is encoded in this place. So this is a square, and this is 1, 1 simplex in our bisimplicial set. So let's look how do they look in geometric realization. So first one is 0, 2 simplex. So it's just a triangle with 3 sides. Each of the sides is visible from here. So one is inclusion of empty to M. Another one is also inclusion of empty to M. So 2 sides are just the same and they are identified in the geometric realization. And third side is given by F. And I hope it's not confusing. Oh, sorry. So, and in terms of vertices, it has 2 different vertices, empty and M. So in geometric realization, it looks like a cone where this is 2 sides from empty to M, just inclusion, and the base of the cone is given by this hooked arrow from M to itself, labeled by F. So this is how the first simplex looks in geometric realization. So second simplex is 1, 1 simplex. Again, it's very straightforward to see what are the edges of this 1, 1 simplex. So one is degenerate. So this one is just degenerate. And then there are 2 sides that are inclusions from empty to M, but note that before we also had a side that was inclusion from empty to M, but it was labeled by a different arrow, and this is important. So even though, and again, the fourth side is this hooked arrow that's labeled by F, and in geometric realization, it is again a cone, but it is a different cone. it also has one of the vertices empty, another M. Base is also hooked arrow labeled by F, so it's the same, they have the same base. But the different, why is it a different column? Because this inclusion from empty to M is different. So this is how in the geometric realization the second Chi looks. And if you look at simplex 1 and 2 together, you see that they have the same base. So if you glue them, it's just S2, well, with also 2 points identified. So this is copy of S2 in our geometric realization. And this is by definition, so 1 plus 2, 1 union 2 is my definition of this element in K1. So it is some element in K1. It's also based at empty set. So it's exactly what we want. But the question is, well, I showed you that there is some element, but is it good? Maybe it's trivial. And the statement is that, yes, it's nice. It sees something about manifold and how different work is. So let me show you what does it see. So I told you that literally by now the only method how we can see that something is non-zero is either using this sphere spectrum or K-series of integers. And we will use the second one. So we will use our map to K1 of integers, which is Z2. So I will show you where this element in K1 of Z, which is Z2, what is the image of this element. So we take this construction and track where does it go in K1 of Z. And I will explain a little bit how to trace the image. So let me first tell you the answer, so where it goes, and you will see that it can be non-trivial. So it will depend on two parameters, dimension of M, and if F is orientation preserving or orientation reversing. And so orientation preserving, orientation reversing. And in this case, it will be determinant of Fk. So what is Fk? F was a diffeomorphism from M to M. So it induces a map on homology for each K. And I tell you, let's only look at the middle dimension. So only for, if my manifold is 2K dimensional, then let's look at HK. And then F induces something there. And we only take the part that is non-torsion. And then the determinant is plus minus 1. And this is what the image of the constructed element sees. It sees this determinant in the middle dimension. So in this case, where M is odd dimensional and F is orientation preserving, it's trivial. So now I look at Z2 multiplicatively. So 1 means trivial element. If I have orientation reversing case, then, oh, sorry, let's look at M odd dimensional. Then it gives finally semi-characteristic. So semi-characteristic of a manifold is, so now I'm working mod 2. This is not exactly the usual definition, because in the usual one you should take signs into account. And here for me it doesn't matter what signs are. So it is sum of Betti numbers up to middle dimension and mod 2. So it doesn't have to, in general, semi-characteristic doesn't have to be mod 2. But in this case, since we work mod 2, we just see semi-characteristic mod 2. And in the case that is left, we see a product of determinant in the middle dimension times semi-characteristic. Well, usually semi-characteristic is not defined. Well, it is defined, it can be defined, but usually it doesn't appear in anywhere in even dimensional case, as far as I know. And this is why usually people write it in odd dimensional case only. But still, this is what happens. We can write this expression up to middle dimension, and this invariant C is the product. And maybe I was a little sloppy here, because here it looks like I'm summing Betty numbers additively, and I said that I want to see everything multiplicatively. So to make it completely fair, I should do this. -1 to the degree of semi-characteristic, and the same here. So now this is fair. And let me tell you just a few words how this expression appears, what's going on. So actually it's not hard to trace what's going on, and the construction was just designed in a way such that we hit some generators in K of Z. So what's going on? We have to look at those two simplices that I showed you. So this one, these two, purple and green. And by definition, by the construction of how the map to K of Z works, this guy goes, so this class, this sphere, it goes to the following map of chain complexes. So you take singular chain complex of M, and you see, you look at what F induces on this chain complex. So this now lives in K1 of homologically bounded chain complexes. And then if you want to translate from chain complexes to just modules, what you do, instead of looking at the whole complex, you have to sum even dimensional homology with corresponding F on it, and subtract odd dimensional homology. So now, in this case, I am thinking of elements in K1 of Z given by pairs module and automorphism of the module. So this is something that lives in K1 of Z. And then, oh no. So now I want to, I know that K1 of Z is just Z mod 2, and I want to see which exactly element I'm hitting when I'm looking at this expression. And there is a very classical translation. So if I want just to think which element in the 2 it hits, I have to take product of determinants. So it will be determinants of corresponding FIs. And so in general case, if it were not Z2, it should be signed product of determinants. So determinant of Fi to the power minus yes, minus I. But since we are working, sorry. So the formula would be like this. Since we are working with Z2 coefficients, it doesn't matter. So I will just remove the sign. So this is a product of determinants of FIs, and FIs is something that is induced on homology. And then there is this is a very nice exercise in Poincare duality. So you can just show that, so this product of determinants is something that lives in the 2, but now it's a little too bulky, and you can make it much neater if you notice that this product is just determinant in the top dimension and in degree dimension of hi, so I is Betti number. So this is nice exercise in Poincare dual. So nothing really fancy here. But then when you arrive at this formula, you can just see that Fn is your top dimension and it's plus minus 1. So either orientation preserving or orientation reversing. So if it is orientation reversing, then it's minus 1 to the power of Betti numbers. And I think I somehow missed. Yeah, okay, yes, everything is correct. Okay, so this is a kind of fast explanation how to go from the element, how to trace where it goes to in K of Z. So next part, let's talk a little bit about topological version of K series with squares and how it is related to BCob. So what is this topological version of squares? When we defined bisimplicial set, we never took into account any topology on embeddings between manifolds. But if you take that into account, and also Rina mentions this in her talk, then suddenly you are not in the world of bisimplicial sets, but you are in the bisimplicial spaces. And it's also a spectrum, and it's also a nice spectrum, and theoretically, hypothetically, it sees more because it also encodes topology. So far, we don't really know if those spectra, so K-top, and the previous one, are they different or not, so discrete and topological version. But what we know, so this is also in our paper with Carmen and René, that K naught is the same. So K naught of topological squares of manifolds. And in our paper, we were denoting it by writing a bar over manifolds. But I'm sure everyone will forget this, so I will be writing topological to emphasize that this is a topological version of squares. So we know that if you do this construction and you take topology into account, and I'm not spending time on saying technical details of topology, but you kind of can imagine that there is topology on embeddings between manifolds. So if you do this construction for bisimplicial space, take loops of this, take geometric realization of this bisimplicial space, take loops. This is your K-top. So K naught is just the same as before. So discrete version, and it is still SKM delta. So our cut and paste groups. But now when we have a topology on K squares, we can relate it very directly with BCob. So let me remind you what is this. So we look at topologically enriched category of coborgens, objects in this category. So let me remove B first and talk about category a little. So objects are n-1 dimensional manifolds embedded in R infinity. They they're not allowed to have boundaries, so objects are closed. And morphisms, well, I'm sure you all know coordinate category, but still. So morphisms are n-dimensional manifolds, and now you take into account the topology. So this is now a space. So for each two objects, you have a space of morphisms between them with topology taken into account. So now I claim that there is a very natural map from classifying space of CoB n to that bisimplicial space, realization of bisimplicial, sorry, not realization, just, yeah, okay, sorry. So to realization of bisimplicial space, and by bar over B, I want to emphasize that now we are in topological case. Maybe the better notation would be to write B top. And if I would, so if I have this map, and this will be a simple, so here I wrote already everything on geometric realization, but it will be a simplicial map of simplicial spaces. If I take loops, I will have a map from loops BCob to K squares topological of manifolds. So since, sorry, I messed up. So the map is very easy. Let me just present it. So as I said, I will be constructing a simplicial map from nerve of the category CoB n to the diagonal. So now I want to make my bisimplicial space into simplicial space by considering its diagonal. And this will be, so our construction will be a simplicial map. So what we do, we have to subdivide the left-hand side. So it's edgewise subdivision. And let me remind you that whenever we have a functor, so whenever we have a simplicial space or set, so both work. So whenever you have a simplicial set F, you can consider its subdivision, and it is given by doubling of your n simplices. So you take n, you send it to n times n op, and then you join those two copies of n. It will be 2n plus 1 simplex, and then you apply f. And this is subdivision. And on geometric realizations, so if you take f and subdivision of f, realize them both, it will give you homotopic results. So when I take subdivision, well, not even homotopic, homeomorphic. When I take subdivision of the left-hand side, I'm not changing geometric realization at all, but I'm a little bit changing my simplicial structure. So what was the new k simplices here, they will be old 2k plus 1 simplices. So the construction is you want to take k simplex in the subdivision, which corresponds to 2k plus 1 simplex in the nerve. So what is 2k plus 1 simplex in the nerve? it is a string of composable cobordisms of length 2k plus 1. And this I will write in this shape. So this is of the length 2k plus 1. I just numbered them differently. And such 2k plus 1 simplex should go to, so I want to send k simplex to k simplex in diagonal. So this should be some k by k square of push outs of manifolds. And here it is. So you just attach one by one cobordisms where those labeled with prime, they go vertically, and those without prime labels, they go horizontally. And since in cobordisms, this is just attaching, then of course it will give you a push out. So I'm not writing everything, but you can imagine what's going on. So on each step, horizontally, you attach one cobordism on the right, and on each step vertically, you also attach one cobordism that's labeled by prime. And you can extend it to the whole k by k square. Okay, let me stop on this. And so on. So I'm writing somehow diagonal, and I'm not claiming that it is enough to specify diagonal. But in this case, it's completely clear how to extend from diagonal. So you just horizontally, this part is happening, and vertically attaching of this thing is happening. And I claim that this map is simplicial, and on pi naught, so you remember it was a map from loops BCob n to k squares topological. So now I can take pi naught of both sides and see what happens. So on the left hand side, loops of BCob, pi naught of that is pi 1 of BCob. And this is so-called SKK groups. And this was mentioned in Carmen's talk. So let me not remind you what is this, but this is kind of, it is almost the same, very similar definition to SK, but with less relations. So there is a map from there to the usual SK without boundary. And this is a surjection. And then we know that SK without boundary, they inject into SKN with boundary. And this is the map that's induced on pi naught. So left-hand side has pi naught SKK, right-hand side, that is k square stop. It has pi naught given by SKN boundary, so cut and paste groups. And this is this natural map. So it's this map on spaces does exactly what we would expect it should do on groups. So next part that I want to talk is about k cubes and BCob n plus 1. So maybe you notice that like previously it was k squares and BCob n, so it's important. So n-dimensional k theory of n-dimensional manifolds was compared with BCob n, and when we have cubes, it will be compared with one dimension higher cobordisms. So I have like 3 minutes, and let me remind you that there was a map in René's talk from cobordisms, group of cobordisms, to n bar. So skn bar is a sk group, but with extra relations that you also identify manifolds that are coborded. So it's even smaller group. And there is, of course, a natural surjection from group of cobordins to sk bar. So this was discussed. And we introduced a version with boundaries. So we introduced a notion of, this was discussed in the René's talk, that there is a notion of cobordins with trivial boundary, where you, as objects, you allow manifolds with boundary, but you say that cobordins have to be trivial on the boundary. So they should be diffeomorphic to cylinders. And then you also have a map from this group of cobordins with trivial on the boundary to the corresponding sk bar group. And let me tell you, so let me remind you what was this corresponding spectra that was spectrifying sk bar boundary. So it was called k cubes of manifolds. And it was called cubes because it was coming from trisimplicial space, where we had 3 simplicial directions, and one of them was cobordins. So the building block, so it was also constructed from diagrams of the corresponding shape. So just big diagrams of size KLM, and these were your KLM simplices, trisimplices. And horizontally and vertically, everything was just given by embeddings of manifolds. So all my dots on this unclear picture, they are manifolds. And third simplicial direction was given by cobordins, and of course of one dimension higher and with corners. So okay, it's very unclear picture, but René had a nice one in her talk. So cubes, in a sense, cut and paste of cobordins, where your cobordins are very restricted, and those cut and paste are also quite restricted. So it's not any inclusion, but very nice inclusions are allowed. And then we were noticing, so it was also discussed in René's talk, that you can just look at cobordin direction, and then cobordins, n+1 dimensional cobordins, they live as 0, 0 dot. So it's a simplicial subspace of this trisimplicial space, where you forget 2 simplicial directions. And the map that was induced by this inclusion was just a 0 map on pi naught, which is not a big surprise, because if you think of what's going on pi naught, the right-hand side, sorry, from what? So the map was not from BCob n+1 to k cube, it was from loops, because we have to loop everything. So pi naught of the left-hand side is skk n+1, and pi naught of the right-hand side is skn boundary bar, and dimensions don't fit. So there is no natural non-zero map. So it's not a big surprise that this map that we constructed on the level of spectra on pi naught, it was given a 0 map. Unfortunately, I don't have time to describe the construction, but what we did with Mona and George, so we constructed a map not from loops of BCob n to k cubes, but just from BCob n+1 to k cubes. And it is not a simplicial map, it is a map just on geometric realizations, but it does, so let's call this map, I don't know, alpha, since we are not discussing the construction, let me just tell you that the map just does what we want on Pinode. So it's a good map, I guess. So on Pinode, on the right-hand side, we have omega n, so group of coordinates, and on the left-hand side, it's skn bar, and there is such a map. So it's a very well, it's a map coming from this. And also there is no reason to say that we have to restrict to BCob n where objects are closed. So we can add this boundary condition where boundary means a trivial boundary, and then this map would correspond to this green map that was discussed in René's talk. So we somehow filled this gap that we spectrified the map, this natural map of groups. Thank you for your attention.
Thank you, Julia. Thank you very much. Very nice talk.
Thank you.
So, questions?
I'm very curious what the map looks like.
Well, it will take like 10 minutes. I'm sorry.
Explain it to me.
I'm sorry. We have to give one more talk. Okay, no worries. I will explain it to you.
Okay, so you can add boundary, but do you need to add boundary in order to?
No, you don't. So there is a map from BCob n+1 to, so from closed version, but there is also a version where you add boundary, so you don't have to add boundary.
And then it's from the monoid, I assume, the trivial boundary proportion monoid.
No,
that's Pinode. But the Pinode of this proportion category is a monoid, not the group.
Right. Yes. Okay. Yes, you're right. Yes.
I would like to ask the following, Julia. Well, in this part, when you have this map from BCob to bisimplicial, well, is the bisimplicial cells, that is the square, the key, and then, well, key square top, and then you have a map from key square top manifolds to key of the interiors.
So you're talking about this map that's now on
I was wondering what is the composition map from BCob to K, and then we arrive to key Z.
Wait. To K of Z. Okay, I see. Yeah, okay. I think, so on Pinode, what it is SKK. Yeah, it's, well, it's Euler characteristic.
The Euler characteristic.
Yeah, right. Yeah, for this, you don't even have to know anything, right? So if you just compose, you know that on each level from SKK to SK bound, whatever. So SK boundary, it just kind of taking quotient, and then it's Euler characteristic. So it's, and Euler characteristic is SKK invariant. So it's good.
Oh, okay. So, well, because and there is a paper by Tillman where she defines some functor from Cobb to. Yeah,
okay, I see. Yes, it should agree. Yes.
Yeah, I think that that is has a geometric interpretation, and maybe this is the algebraic interpretation in dimension 2.
Yeah, right. So there is a map from BCob to K. Yes. They should just agree. Yes.
Yeah, that's true. And it is possible that the Bogomolov multiplier appear in somewhere.
Honestly, I don't know. I should really look properly at Bogomolov multipliers. So far, I have no idea. So I really have to read about it. No.
Because well, in the SK overline, yeah, is in dimension to the Bogomolov multiplier, but you have the boundary.
So on SK bar boundary,
yeah. In dimension two, without the boundary.
Yeah. Without boundary. Okay. So on the usual SK bar, okay, you're saying that what? So SK bar.
Sorry, SK bar in dimension 2 is 0.
I know, but with the Equivariant version.
Oh, Equivariant version. Okay.
Yeah.
That is the Bogomolov multiplier.
Yeah. So nothing is equivariant here. Yeah.
There is some exact seconds.
No. No, so SK2 bar with boundary would not be trivial, but yeah, without boundary. So SK bar is somehow why we looked at it, because we wanted to do something with signature. And then as a first try to do something with signature, we just decided to isolate it somehow. And this is what SK bar is doing. Yeah, so this was our attempt to approach signature somehow.
So, any other questions, comments? Not well. Thank you very much, Pia, and also Rene and Carmen.
Thank you, everyone.
Really nice.